Today, we will be discussing the rheology of colloids, specifically how the colloidal particles affect the viscosity of the colloid. There are two main factors of the particles that can affect viscosity. First is the volume fraction of the suspended particles, and second is the surface interactions between those particles. We will first start with the volume fraction. When considering volume fraction effects, particles are assumed to be a hard sphere, with no interaction with one another. Now, when a particle is pushed through a suspension, there is a small drag force dissipating the energy being used to push it faster than if there were no particle at all. It is this increased drag that manifests itself as a higher viscosity in a colloidal system. Albert Einstein was able to quantify the effect of volume fraction on viscosity in the equation shown here, where μL is the original viscosity, phi is the volume fraction, and μs is the new viscosity. We see that this relation holds true, but only for very low volume fractions, around less than 10%. Beyond that, things start to get a little hairier. At higher volume fractions, we begin to see shear thinning behavior in the colloid. In this region, the shear rate is low enough that Brownian motion dominates the motion of the particles, causing the particles to try and move past one another, which leads to lots of drag and increases the viscosity. As the shear rate increases, we move into the shear thinning region. Here, the shearing overtakes Brownian motion and begins to force the particles into more ordered flow patterns, like strings or sheets. These flow patterns minimize particles' interactions and drags as they flow past one another, thus decreasing the viscosity until reaching a lower plateau. Increasing the shear beyond this plateau begins to break down the flow patterns with turbulence, forcing particles into one another and drastically increasing viscosity. Colloids at high volume fractions, near the packing limit of the particles, are particularly susceptible to this problem. Now that we've seen the effects of volume fraction, we need to look at the other factor, surface interactions. If particles interact with one another, they can either be repulsive or attractive. Let's start with the repulsive particles. For the most part, they behave just like hard sphere particles, exhibiting the same linear increase of viscosity with volume fraction and shear thinning behavior, except the viscosity is always slightly higher than that of a hard sphere colloid. This is due to the formation of an electric double layer around the particle caused by the surface charge, represented here. This layer entrains the fluid inside it and causes the particle to behave as if it had more volume than it truly does. To account for this, we use an effective volume fraction, which includes both the particle's true volume and the volume of the electric double layer. Using an effective volume fraction, repulsive particle behavior matches hard sphere behavior quite well. Attractive particles, on the other hand, have some unique behavior due to the particles coming together at rest. This produces higher viscosities than hard sphere colloids, a yield stress to initiate flow, and very pronounced shear thinning effects. The yield stress is caused by the stable network of particles that is formed at rest. Some amount of energy is going to need to be introduced to break the initial attractive forces between the particles and begin flow, shown here. Continuing from that, we see drastic shear thinning as shear rate increases, because the large chunks of particle network that entrain lots of fluid inside them are being broken into smaller and smaller chunks, freeing up fluid and easing the flow. So that covers the basics of colloidal rheology. I hope you learned something and are ready to dive into more complicated colloidal systems.